Welcome to the university. In this video we are going to study the brief history of our solar system. But before anything else, please like this video, share our contents, click the subscribe button, and don't forget to hit the notification bell to get updated when we post new videos. We will take you back in time when the solar system is just on its early stage of formation. According to scientists, the prominent hypothesis acceptable to explain the origin of the solar system is the Nebular Hypothesis. This suggests that the entire solar system first formed in a nebula. Scientists are also observing the same phenomena that is happening in the universe. They observed that the processes that created our solar system have also created an uncountable number of other solar systems. The Nebular Hypothesis details the process how a solar system can form from a large gas cloud, called as nebula. The nebula begins to condense. Most of the mass is in the center. There is turbulence in the outer parts. The turbulent eddies collect matter measuring meters across. Small chunks grow and collide, eventually becoming large aggregates of gas and solid chunks. The evidence of this hypothesis is seen from the pictures from the Hubble Space Telescope. It shows newborn stars emerging from dense, compact pockets of interstellar gas called evaporating gaseous globules. Gravitational attraction causes the mass of gas and dust to slowly contract and it begins to rotate. The dust and matter slowly falls towards the center. As a result of contraction and rotation, a flat, rapidly rotating disk forms that will become the protosun. Here is a false-colored image of the protostar. The multicolored area shows a dust disk surrounding a newborn star. The red-orange area at the center represents the brightest region, which contains the young star. It is surrounded by the cooler, dusty disk, which appears as yellow, green, and blue. The diameter of the disk is about 20 times larger than our entire solar system. After sufficient mass and density was achieved in the Sun, the temperature rose to 1 million degrees Celsius, resulting in thermonuclear fusion. It resulted to the fusing of two hydrogen atoms to form one helium atom plus an amount of tremendous energy. While the Sun is forming, eminent activity is also seen in the vicinity of the protostar. The enveloping disk of gas and dust forms grains that collide and clump together into small chunks or planetesimals. These planetesimals are said to be having a diameter of almost equal to 1 kilometer. The successful planetesimals are the seeds of the protoplanets. Gravitational forces allow the inner planets to accrue and compact solid matter, including light and heavy atoms. Solar radiation blew gases, primarily hydrogen, helium, away from inner planets. These gases were collected and condensed into the gas giants, Jupiter, Saturn, Uranus, and Neptune. Beyond Neptune, ice and frozen gases form Pluto, Sedna, and the Kuiper Belt objects. Leftover debris form comets and asteroids. The inner planets were formed in different manner relative to the outer planets. The terrestrial planets build up their size through multiple collisions, and accretion of other planetesimals by gravitational attraction. Giant outer planets grew by gas accretion. Here are the size comparison of planets. Here is size comparison of Venus, Earth, and Mars. These maps are color-coded to display different elevations on the surface of each planet. The age of the Earth is said to be 4.57 billion years old. Evidence like the meteorites give us access to debris left over from the formation of the solar system. We can date meteorites using radioactive isotopes and their decay products. As a result of radiocarbon dating and uranium dating, scientists were able to create a geologic timeline. This shows the chronological order of events starting from the formation of the Earth. The primitive Earth is inhabitable for any life form. For the first half-billion years of its existence, the surface of the Earth was repeatedly pulverized by asteroids and comets of all sizes. One of these collisions formed the Moon. One hypothesis that offers an explanation how the Moon is formed is called the giant impact hypothesis. This hypothesis predicts that around 50 million years after the initial creation of Earth, a planet about the size of Mars collided with Earth. This idea was first proposed about 30 years ago, but it took calculations by modern high-speed computers to prove the feasibility. According to this hypothesis, the collision is very spectacular, and a very considerable amount of material was blown off into space. Most fell back to Earth due to its gravity. The other debris formed another body that is also caught in the Earth's gravitational field. This body eventually became the Moon that we know today. This hypothesis also offers an explanation why the Earth is tilted. It also claims that the Moon formed just like the way how the inner planets were formed. Part of the material from the collision remained in orbit around the Earth. By the process of collision and accretion, this orbiting material coalesced into the Moon. The early Moon orbited very close to the Earth. Heat increased in the inner part of the early Earth. This is explained by three factors. The first factor is the frequent collisions that transfers kinetic energy. This kinetic energy is converted into heat. The next factor is by mechanical compression. The inward pull of gravity causes heavy elements to sink into the depths of the core. And the last factor is the radioactivity of elements such as uranium, potassium, and thorium. In this way, the core of the young Earth is formed. It is said that, about 100 million years after initial accretion, temperatures at depths of 400 to 800 kilometers below the Earth's surface reach the melting point of iron. This is best explained by the process called as global chemical differentiation. The heavier elements, including the melted iron, began to sink down into the core of the Earth, while the lighter elements such as oxygen and silica floated up towards the surface. This global chemical differentiation was completed by about 4.3 billion years ago, and the Earth had developed an inner and outer core, a mantle, and crust. It resulted to 4 distinct layers of the Earth that has a distinctive chemical composition, with the crust being quite different from the other layers. Earth's whole chemical composition is shown below. The distinctive layers are enumerated as follows. Lithosphere is describes as strong, rocky outer shell of the solid Earth including all the crust and the upper part of the mantle to a depth of 100 kilometers. It is where the plates are formed. The second layer is called the asthenosphere, which is described as weak, ductile layer of the mantle beneath the lithosphere, deforms to accommodate the motions of the overlying plates. The third layer is known as the mantle, which is further subdivided to the upper mantle and lower mantle. The next layer beneath the mantle is called the core, comprised of the outer core which is said to be molten iron. And it is followed by the inner core which is composed of primarily solid iron. One eminent process that helped in the formation of lands, oceans, and the atmosphere is the process of volcanism. Continents formed from solidified magma that float up above the mantle. Volcanoes spewed out fluid and gaseous outer layers believed to have been created by outgassing of gases and fluids from volcanic eruptions, in a process called volatile transfer. This process is reason why the atmosphere of the Earth have evolved. It is said that right after its creation, the Earth is thought to have had a thin atmosphere composed primarily of helium and hydrogen gases. The Earth's gravity could not hold these light gases, and they easily escaped into outer space. Today, hydrogen and helium are very rare in our atmosphere. For the next several 100 million years, volcanic outgassing began to create a thicker atmosphere composed of a wide variety of gases. The gases that were released were probably similar to those created by modern volcanic eruptions. The composition of the early atmosphere is said to have water vapor, H2O, sulfur dioxide, SO2, hydrogen sulfide, H2S, carbon dioxide, CO2, carbon monoxide, CO, ammonia, NH3, and methane, CH4. Take note that oxygen, O2, gas is not created by volcanic eruptions. It is hypothesized that water vapor escaping from the interior of the Earth via countless volcanic eruptions created the oceans. This took hundreds of millions of years. Astronomers also hypothesized that comets impacting the Earth were a major source of water that contributed to creation of the oceans. Remember that comets are best described as dirty ice balls. The earliest evidence of surface water on Earth dates back about 3.8 billion years ago. The arrow in the geologic timeline shows when the first ocean was formed. By 3.5 billion years ago, when the Earth was a billion years old, it had a thick atmosphere composed of CO2, methane, water vapor and other volcanic gases. By human standards, this early atmosphere was very poisonous. It contained almost no oxygen. Remember, today our atmosphere is 21% oxygen. By 3.5 billion years ago, the Earth also had extensive oceans and seas of salt water, which contained many dissolved elements, such as iron. But most importantly, by 3.5 billion years ago, there was life on Earth. By 2.5 billion years ago, the continents had been formed. The density of the continental crust, equal to 2.8 grams per cubic centimeter, is lighter than the crust found on ocean bottoms, equal to 3.2 grams per cubic centimeter, so the continents rise above the ocean floor. A question that remains unanswered is, when did plate tectonics start?